Hello, and welcome to the video lecture for topic 28, Delocalized molecular orbitals. So we saw in topic 27 how to form an orbital mixing diagram for localized sigma and pi systems. Now, the nice thing for us when we deal with delocalized pi systems, and we'll see a few examples of this as we go along here, is that we can ignore all of the sigma bonding orbitals and sigma anti-bonding orbitals. We just ignore those. And the reason that we ignore those is that it is the pi bonding orbitals and the pi anti-bonding orbitals in a delocalized system that are going to participate in any chemical reaction before any of our sigma bonds or sigma bonding orbitals get involved, right? And so so really, when we have a delocalized pi system, it's all of the pi orbitals and pi anti-bonding orbitals that play the major role in how the molecule behaves. So to get into this topic, and more so again, like with topic 27, this video is designed to show you the mechanics of what you'll be expected to demonstrate for Chem 201 in terms of delocalized pi systems. We're just going to take a look at how to do our molecular orbital energy diagrams and how to draw graphical representations of what those molecular orbitals look like for a couple of different systems. And so the first system that I'd like to start off with us examining is going to be the 1,3-butadiene pi system. And so here we have two pi bonds that are in conjugation with each other, right? And so we can look back, we've seen this pi system before in topics 17, 22, and 23. And so now we'd like to be able to develop a molecular orbital energy diagram to really explain what's happening in this pi system, right? And so we can go through, create a lot of different resonance structures where we're able to delocalize and see what that looks like. But more valuable for us is to be able to do just an energy diagram and cartoon representations of no, I wouldn't say more valuable, but equally valuable for us is to be able to do a molecular orbital energy diagram and see what are the bonding and anti-bonding interactions that are happening in that system really look like. And so when we have this conjugated pi system, or really any conjugated pi system, right, we're only looking at the pi bonds and pi anti-bonding interactions. And so we start off by counting the number of atoms that participate in the pi system. And so here we have 1, 2, 3, 4 carbon atoms that are participating in this pi system. Each of those carbon atoms is donating one p orbital, right? And so since we have 4 p orbitals going in, that means we're going to need to make a total of 4 pi bonds, right? So 4 atomic p orbitals, they mix together to make 4 new molecular orbitals. Each of those orbitals is a pi orbital, and it's either going to be a bonding or anti-bonding. We'll see how to distinguish that here in just a moment. And so once we know how many atoms are participating, we can immediately draw in the orbitals in their various energy levels. So here's 1, here's 2, here's 3, and here's the 4th one. And we'll just label these pi 1, pi 2, pi 3, and pi 4. Now, the next thing we want to do is count how many electrons are participating in this pi system. So we have 2 electrons from this pi bond and 2 electrons from this pi bond. So we have a total of 4 electrons that are involved in this pi system. We're going to use Hund's rule to begin filling in, right? Begin filling these molecular orbitals in with our 4 pi electrons. And so we fill from lowest energy to highest energy, making a completely filling each orbital before we move to the next one, which shows us that pi 1 and pi 2 for 1,3-butadiene are full, and pi 3 and pi 4 are empty. This also allows us to say that pi 3 and pi 4 are going to be our anti-bonding orbitals. And so we use that same symbol, right, pi star, except now we have pi 3 star and pi 4 star. Those are going to be our anti-bonding orbitals. From there, we can also begin to define 2 of these orbitals in a special way. And so when we're dealing with these pi systems, we're very interested in knowing which one is the highest occupied molecular orbital, abbreviated HOMO. And we also want to know which one is the lowest unoccupied molecular orbital, abbreviated LU, LU MO, right? And so we want to know which one is our highest occupied molecular orbital, lowest unoccupied molecular orbital, also known as the HOMO and the LUMO. And so it's very easy for us to find the highest energy molecular orbital that is occupied with electrons is pi 2. So pi 2 is our HOMO. And our lowest energy unoccupied molecular orbital is pi star 3, which is going to be our LUMO. And so we can now label those two orbitals with these descriptors that are going to be important to us when we get to Chem 202 and beyond. And so all that's really left is for us to be able to draw, a graphical representation of what the bonding and anti-bonding interactions in each one of these orbitals is. So let's go ahead and do that. We start off with pi 1, which has 1, 2, 3, 4 carbon atoms, each donating a p orbital. And our lowest energy orbital, right, pi 1, we are going to have all bonding interactions there, right? And so we're going to want to shade our orbitals, and we have all we have all bonding interactions, and we denote that by drawing these lines between the lobes of a p orbital to show that we have all bonding interactions, right, between all 4 p orbitals, both above and below, in our lowest energy molecular orbital, pi 1. For pi 2, we're going to repeat this process, but every time we increase in energy, we introduce one instance of an anti-bonding interaction. So here now in pi 2, I have one instance of anti-bonding interaction, or also known as one node, and that's going to be right down the center of the pi system. This is now my node. And so now we can say that between these 2 carbon atoms, we have a bonding interaction. The node indicates that we have a anti-bonding interaction, and we further indicate that by switching how we shade our p orbitals. And so we have bonding interaction on one side of the node and bonding interactions on the other side of the node. Now we can move on to pi 3. Right, so this is going to be pi 3. And again, we're going to put in our p orbitals. Now pi 3, we've gone one step up again. So this is pi 3 needs to have 2 nodes. There's one of my nodes. There's the other node. And so now we see that between this first carbon and second carbon, we have an anti-bonding interaction. So I have to switch over which side of them I'm shading. Between my 2 central carbons, I have a bonding interaction. And then finally, my node here indicates that I have an anti-bonding interaction between these 2 carbons. And so I switch my shading once again. Finally, I'm just going to move over here due to space, but for pi 4, I can repeat this process one more time. So here now I'm going to do pi 4, and both pi 3 and pi 4 are anti-bonding interactions. And we'll get back to that in just a second. Right? So let's see now, we've gone from pi 3 to pi 4. That means we need to add one additional node. And so that puts one node between each of the carbon atoms. And so now we can go in and shade, fill in our p orbitals. and we see that the shading switches as we move from one carbon to the next to indicate that there are 3 antibonding interactions. So these cartoon or graphical representations of each of these molecular orbitals also give us an indication as to which of these molecular orbitals are bonding and antibonding. A bonding molecular orbital will have more bonding interactions than antibonding interactions. And so if we look here in pi 1, we have 1, 2, 3 bonding interactions. So this is a fully bonding orbital, whereas in pi 2, we have 1, 2 bonding interactions and 1 anti-bonding interaction. So our bonding interactions are more than our anti-bonding interactions, and pi 2 is also a bonding molecular orbital. Next, when we come to pi 3, we see that we have one bonding interaction and 2 anti-bonding interactions. That means our anti-bonding in pi 3 exceeds our bonding, and that means that pi 3 will be an anti-bonding molecular orbital, and it gets that designation star, right, pi 3 star, to indicate it's anti-bonding. And so finally, when we come to pi 4, we see we have 0 bonding interactions. All 3 of our interactions are anti-bonding interactions, as denoted by our dashed lines that represent nodes. And so pi 4 is a fully anti-bonding molecular orbital, and it gets a star as well. Okay, so what I'd like to do now is move on and show how this system can be used to represent charged or radical species as well, right? We've looked at something that's completely neutral here, but we can also use this method to produce a molecular orbital diagram and cartoon representations for systems that have a charge, whether it be a positive charge, negative charge, or for systems that have a radical species as part of the pi system. So I'm going to clear off the board, and next up we're going to take a look at a allylic cation. Okay, so as I said, let's now take a look at how we can represent an allylic cation, right, using a molecular orbital energy diagram. So we need to remember now that there is, on our carbocation, there is in fact an empty p orbital there, and this system can engage in resonance, as we've seen earlier this semester, to delocalize that positive charge, right, on both ends of that allylic cation. And so really here now, when we do the first step of our analysis, counting how many atoms are involved in the pi system, we see that we have 3 atoms, right? We have 3 carbon atoms that are contributing to this pi system. However, we only have 2 electrons. So since we have 3 carbon atoms, each giving a p orbital, that means we're going to form 3 pi molecular orbitals that are only going to have 2 electrons in them. So we, again, can just start off with, here's pi 1. We can put in now pi 2. We can put in pi 3. And we can put our electrons in 1, 2, and just pi 1 is filled. We can label pi 1 as our HOMO, and we can label pi 2 as our LUMO. But you'll notice now that I haven't actually begun to introduce which of these are bonding molecular orbitals and which are anti-bonding molecular orbitals. And I'm going to wait to do that until after I do my graphical representations, because that's going to give me a much better sense of how many bonding and anti-bonding interactions there are. So let's go ahead and start the process for pi 1. We have 1, 2, 3 carbon atoms involved in pi 1. Each is going to give a p orbital to that. And we know that consistently always our lowest energy molecular orbital, no matter which one it is, the one that's lowest in energy, here now pi 1, is going to be a fully bonding molecular orbital. So I've just arbitrarily decided that I'm going to shade my upper lobes of my p orbitals, and I indicate bonding by connecting those p orbital lobes with lines. So this is now pi 1. And I see that I have two bonding interactions, 0 anti-bonding interactions. That means that pi 1 is a bonding molecular orbital, fully bonding. When I come now to look at pi 2, so here now we're going to go take a look at pi 2. I need to figure out where I'm going to introduce my node. And my node needs, since I only have one node in pi 2, it needs to divide my system in half. And it turns out that node actually resides right on that central carbon atom. And we have no bonding interactions whatsoever. We just shade opposite each of these, right? But there are no bonding interactions in pi 2, which means that pi 2 is going to be an anti-bonding molecular orbital. And we can designate that as pi 2 star. Finally, for pi 3, I'm going to need to have two nodes. This time, however, I can place one node between each of the carbon atoms. Again, I'm going to have no bonding interactions whatsoever. My shading can remain constant. And pi 3 is now a pi 3 star, which is an anti-bonding molecular orbital. And I can come back here now to my energy diagram, and I can see this. Right? So this is how we can do this for a system where we have three molecular orbitals, but we have a charge, and so we only have 2 electrons. The other thing that we can do, and I'm just simply going to modify what this picture looks like, is to say that instead of having a cation, an allylic cation, instead now I'm just going to say that I have an allylic radical. Right? And so we encountered radicals earlier in the term, and now we can still show that we have resonance delocalization of that allylic radical. Our arrows are slightly different. We use our fishhook arrows to show that delocalization. But we still do have, right, delocalization of that cation across all 3 atoms. And now we can change down. We still have 3 carbon atoms, each donating a p orbital. We're still going to have 3 pi molecular orbitals, except this time we're going to have 3 electrons. So I just need to add 1 electron to pi 2, an anti-bonding molecular orbital. My graphical representations don't change, but I can add now a second descriptor to pi 2, a second descriptor for pi star 2. It is not only it now is no longer our lowest unoccupied molecular orbital. Pi 3 is our lowest unoccupied molecular orbital. And pi 2 becomes what we call a SOMO. And SOMO stands for singularly occupied molecular orbital, which means that it is a molecular orbital that only is half filled. It has a single electron in it. It is a SOMO, so now we have a HOMO, a LUMO, and a SOMO. And we can now describe these to help us predict how things are going to react, which you'll learn in future organic chemistry courses. So really, that is the whole kit and caboodle. What will you be expected to demonstrate? Given a pi system, or a drawing of a molecule that has a delocalized pi system that has conjugation in it, whether it is neutral, cationic, anionic, or has a radical, you'll be expected to generate a molecular orbital diagram, energy diagram, such as what we have here in the center, and draw graphical representations of each of those molecular orbitals, right, showing the bonding and anti-bonding interactions. Okay. So turns out this is our last video lecture for the semester. I'd like to one more time thank everybody for trying out this new teaching style with me. And as always, if you have any questions, please feel free to bring them to conference, lecture, office hours, or stop by, make an appointment to stop by and see me one-on-one. Thank you very much.